Hey guys, thanks for tuning into CMTEQ channel. This is tutorial number 6 on short circuit current and MVA calculations. Now the topic of short circuit analysis is a very crucial topic in power system. This is why we deal with this topic by solving short circuit current and MVA problems. Now in this tutorial 6, we are asked to calculate the safe minimum reactance of the transformer in the system as shown. Where is the system? Here is the system. Okay? If the rapturing capacity of the circuit breaker is 300 MVA, and hence find the short circuit current per machine under this condition. Okay? So the short circuit current that we need to find per machines are those machines here. So these three machines here are what we call synchronous machine. So synchronous generators. Okay. So that the short circuit current we need to find that each machine is supplying. But before we get there, they say we need to calculate first the safe minimum reactance. Okay. As you can see, this transformer here, that is the main transformer that's supplying the load here. And there is a circuit breaker after the transformer, and we are told that the circuit breaker here have a rapturing capacity of 300 MVA. This is the maximum MVA that this circuit breaker can interrupt, okay, the maximum fault, okay, or power that this circuit breaker can interrupt without exploding. Now if you go over this 300 MVA, that means the circuit breaker will not be able to interrupt that fault, but it will rather explode. Okay, that means the whole system will be exposed, so it won't safely interrupt it. This is why you have to ensure that a circuit breaker that is included in your circuit for protection have a maximum rated rapturing capacity that can withstand the fault that is the potential fault that will be present in the system. Okay, now before we continue, please don't forget to like this tutorial if you find anything useful, and subscribe to CMTEQ channel. That will be highly appreciated. And if you have any comment, please drop it in the comment box. Okay, so the following is an illustration of this network. We've got a representation of our three generators. Okay, they are mounted in parallel, so they're supplying the power that is coming into the load here. So we've got a load here. So this section, there is a load here. And from our problem statement here, we are told that there is a short circuit here at this point. Okay, so the short circuit is occurring just before the load there. So the load is not getting any power. And the minimum reactance we need to find is for T1. Okay, that is supplying the circuit breaker that has a rapturing capacitor of 300 MVA. Okay, so this is a short circuit current calculation problem. But before solving that, you need to convert your network into a per unit or an impedance equivalent diagram. And we've done a lot of tutorial on that. And if you are not familiar with per unit system, please check on my channel. I do have a playlist dedicated to per unit calculation. So without wasting any further time, we have to start solving this problem. And to convert this network into an equivalent per unit diagram or impedance diagram, we need a base MVA. Now we can see that the three generators are each rated at 50 MVA. So we can then use the 50 MVA as the base MVA for the entire system. So this means that if 50 MVA is the base MVA, using the per unit formulas, we can then deduce that generator G1 here, per unit, new per unit would be equal to 0.3 because the old per unit is 0.3, and the new MVA base here is equal to the old MVA base. So the whole equation cancel out and we got the old per unit is equal to the new per unit. Noting that the entire zone here, okay, that is zone 1, have a voltage rating of 33 kilovolt. That is a voltage being supplied by each one of these three generators. And zone 2 is rated at 132 kilovolt. That is at the secondary of the step up transformers. Okay, so having said that, G2 will equally be equal to 0.3 J per unit, and that will be the same for G3. So now we've calculated the per unit of all these three generators, and we can then go ahead and draw the per unit equivalent diagram, okay, because we do not have the X% reactance. That's actually what we need to calculate here. So drawing that per unit equivalent diagram will be helpful for us so that we can calculate the Z per unit total. And from the Z per unit total, we can deduce so that we can see if we can find the X% reactance. So that equivalent diagram is as below. So we've got the three generators in parallel, which each one of them having a 0.3 J per unit, okay? And they are all in series with the reactance of this transformer, okay? That from here, we can then calculate this parallel combination, and that will give us a 0.1 J per unit. So the three generators combined in parallel gives us an equivalent per unit of 0.1 J per unit. And that is in series with the X reactance of this transformer. Now we have to remember that this X% reactance that we are missing, that is an unknown in this equation here, is the old per unit of this transformer. Just like these ones here, okay, these ones are the old per unit of these generators that we use to determine the new ones, okay? And this X% is the old per unit of this transformer. So which means we can then go ahead and calculate the per unit of the transformer while having this X% here as the old per unit in that formula of the per unit calculations. So the per unit formula goes as follows. Z per unit new is equal to Z per unit old times SBN, that is the base MVA new, over SB old, that is the base MVA old, okay? And times VB old, that is the base voltage old, over the base voltage new over whole square. Now, in the case of VB old and VB new, we know that this transformer primary, okay, is receiving a 33 kilovolt, okay? So this entire zone here is 33 kilovolts. So the generators are also supplying 33 kilovolts. So this means the transformer VB new and VB old is the same. It's 33 kilovolt. And the same will apply in the secondary here. The secondary terminal of the transformer are rated at 132 kilovolt. And the line here is also 132 kilovolt. So VB old and VB new in this transformer here will be either 33 kilovolt and 33 kilovolt or 132 and 132. I hope it's clear there. So from here, we can then go ahead and replace the value into the formula. Since we do not have the Z per unit old, okay, so we replace it with the X% that we are looking for. Then SBN, that is the new base MVA, that is the 50 MVA that we selected, and the 25 MVA is the 25 of the transformer there, okay? And VB old over VB new, we selected 132 over 132. We could have also used 33 over 33 kilovolt here, and that will give us the same answer. And solving for this equation give us a X% times 2J per unit. So basically, this here is the X% that we're representing there. And this equation here give us a 2. So that is 50 divided by 25 give us a 2. And this one here cancel out. So we have a whole equation give us X% times 2J per unit. Now from here, we can then go ahead and calculate the Z per unit total. So the total per unit impedance will then be equal to Z per unit total is equal to Z per unit of the 3 generator, that is 0.1 J, plus a Z per unit of the transformer. So that is Z per unit new that we just find here, that is X% times 2. And this combination will give us 0.1, okay, plus X% times 2. So we just replace with the value. And we can then deduce this as 0.1 plus X% times 2. So that is Z per unit total, okay. So the new equation here shows us that we've got two unknown here. The first unknown is Z per unit total. The second unknown is the X% that we are looking for. So, but we know that we can easily calculate the Z per unit total here. Okay? But the problem statement says we are looking for the safe minimum reactance of the transformer. That is the X% of this transformer. That is this one here. So which means we have to change this equation so that we can manipulate it to calculate the X% of the transformer. So making X% the subject of the equation will then mean the 0,1 here is then flipped on the other side of the equal sign and it's become a negative. And from here we can then go ahead and make X% the subject of the equations, and that gives us Z per unit total minus 0,1. So that is this expression here divided by the 2. Okay, so this here then give us the equation for solving X%. So that is the safe minimum reactance of the transformer. But we can still go ahead and simplify this expression further, and that is by dividing, okay, by 2, because 2 is a common denominator in this equation here. So we divide the Z per unit total by 2 minus the 0,1 divided also by 2. And solving for this equation yields us a 0,5 times Z per unit total minus 0,05. Okay, now the 0,5 comes from the one that is always here hidden, so that 1 divided by 2 gives us 0,5. Okay, times Z per unit total, and the 0,1 here divided by 2 gives us 0,05. So this is the expression of X% that we're going to use to calculate the value of this X% reactance that is missing. So from this expression, we can see that the only unknown quantity here is a Z per unit total. So that is the total per unit impedance of our network. So we have to now go ahead and find Z per unit total. Now we know that Z per unit total can be drawn from the formula of the I per unit, which is 1 over Z per unit total. That way, we know Z per unit total will be 1 over I per unit. Now, what is I per unit? We can further calculate I per unit with this formula of the short circuit current that gives us I per unit times I line. And from this equation, we can further deduce that I per unit is equal to I short circuit over I line. So now we need to find the I short circuit and the I line, which is the base current, to determine the I per unit. Once we get the I per unit, we can then replace it into the Z per unit total formula and boom, into our expression, and we find our X. So now what is the way forward? First, we need to calculate the I line, which is the base current. So I line is flowing from this point and down on the secondary of the transformer. But you have to understand that this is a transformer, so the primary current here is not equal to the secondary current. So obviously the secondary current here will be less, okay, compared to the primary current. But which line current are we going to use in this case here? Well, you guessed it. We're going to use the line current from the secondary side of the transformer because the short circuit is occurring on the secondary. So if the short circuit was occurring somewhere on the primary here, around the generator's connection here, we would have used the base current from the primary. But because we have a short circuit occurring on the secondary of the transformer, then we have to use the base or line current of the secondary. So which means our I line formula here, okay, will then be used with 132 kilovolt voltage. Okay, because it's a step up transformers. So from those we can then deduce that our line current is equal to 218.7 amps. Okay, I hope it's clear. Because if you calculate I line here with a 33 kilovolt, you're going to have a bigger current, and that bigger current will result in a different I per unit, and your answer is going to be wrong because your fault is obviously on the secondary, not on the primary. Now that we've calculated I line, we can then go ahead and find the I short circuit. That's the only current we need in order to then find our I per unit. Now, how do we calculate the I short circuit? That is basically the short circuit current that's flowing here. How do we calculate that? But we know that from our previous tutorial, we have calculated the short circuit current, deducing it from the short circuit MVA formulas also. And since we have a 300 MVA rapturing capacity of the circuit breaker, this means that we have to deduce our short circuit current from that short circuit MVA formula. So what I'm saying is that the short circuit MVA formula is given as follow. That is the square root of 3 times VB zone times the I short circuit. What is VB zone here? VB zone is obviously the 132 kilovolt because we are on the secondary zone of the transformer. So from this formula, we can then deduce that our I short circuit will be S short circuit. So that's a short circuit MVA over VB zone times the square root of 3. And D short circuit MVA here is the 300 MVA that we have to make use of. No any other. You cannot use the 50 MVA base value that we are using for the entire network here. You have to use the short circuit MVA because that is what is limiting the capacity of this circuit breaker. And from here, everything becomes so clear. You can just go ahead and replace all the values into your formulas, and you find a short circuit current of 1312. So that basically 1.3 kilo amps of short circuit. Now we've got all the ingredients necessary to calculate our I per unit. We can then go ahead and replace in the I per unit formula I short circuit over I line. So that is 1312 over 218. That gives us 6 amp. So we've got a I per unit of 6 amp. From here, we replace it into the Z per unit total formula. Then we find 1 over 6. That gives us a Z per unit of 0.1667 J per unit ohm. Okay, now from here, it's very simple. We now have Z per unit total. Now we bring our expression, okay, that's the X expression, and we then replace the Z per unit total into our expression, and that gives us a simple mathematical calculation of 0.03335, and we need to put it in percentage, okay, because it's in percentage there. So we have to multiply it by 100, and that gives us a 3.335%. And this is the safe minimum reactance of the transformer that they ask us to calculate, the X% reactance. So all this means is that this value of X% is making sure that the short circuit MVA here is limited to 300 MVA, because this X% value is coming from the Z per unit total. So the Z per unit total is the total impedance that is limiting the current in the circuit here. So if you decrease the value of the total per unit impedance, that means the current, the short circuit current here will increase, and the resulting increase in short circuit current will also mean that the short circuit MVA here will also increase. So if the short circuit MVA increase, that means the circuit breaker here will not resist, it will explode. So what this means is that the X% value that we just calculated, that is equal to 0.03335, that we put in percentage equal to 3335, okay, percent, is from the formula of the Z per unit, okay, nu of the transformer that we find, X% times 2, okay. That means this X% replaced into this formula, it gives us 0.0335 times 2, and that gives us a value of 0.0667. Okay, that's Z per unit of the transformer. Now, the Z per unit of the 3 generators, we calculated that it was equal to Z per unit new, okay, of the generators, it was equal to 0,1 J per unit. And Z per unit total, which is given, okay, Z per unit total, okay, is equal to Z per unit of generators plus Z per unit of transformer, okay, and that gives us 0,1 plus 0,0667, and this gives me a value of 0,1667, and this is Z per unit total that we just calculated. So you can see how all these calculations adds up. Now, this means this Z per unit total here, okay, from the formula of Z per unit is equal to 1 over I per unit, okay, which is I per unit will give us 1 over Z per unit. So if you decrease the value of Z per unit, since the generator per unit values are fixed, okay, so if we change the transformer reactance here, this value here, if we change it, we decrease it, that means Z per unit total will decrease. So if you decrease this Z per unit, okay, let's say we say now this Z per unit is 106, let's say it's 0,1067 like this. That means the I per unit value here will be equal to 1 over 0,1067 like this. What does it mean? It means if you calculate it, you're going to have 1 over 0.1067, okay? So that gives you an I per unit of 9.37. You can see that the I per unit of 937 automatically will give you a bigger short circuit current, because your I short circuit is equal to, okay, I per unit, okay, times I line. Okay, your I line is fixed. Your I line is fixed because that's coming from the base voltage of the secondary of the transformer, so it's fixed. So which means you're going to have a bigger short circuit current by doing now 9.37 plus the 218 that we got. So I mean times, not plus, times. So it's times 2118.7. That's a value. So you can see that you're getting a short circuit current of 24967 amps. If you now include this short circuit current into the formula of S short circuit, that is square root of 3 times V base, okay, times I short circuit, and you're going to get a bigger MVA, and that bigger MVA, if we can calculate it quickly, so that's our I short circuit, so times square root of 3 times 132 kilovolt. Look here, you're getting 468.6 MVA, and you can see that the 468 MVA is way bigger than the 300 MVA of rated value of our circuit breaker. So a slight increase on that reactance on the transformer means we no longer can use that circuit breaker. We need to replace the circuit breaker with a bigger one. Otherwise, the circuit will explode. So this is the importance of these calculations. It ensures maximum protection reliability for your system. Okay, so the next thing now is to then calculate, okay, the short circuit current per machine under these conditions. So that is the current, okay, that these generators are supplying under which conditions? Under the short circuit condition. Because remember, the current these generators are supplying under normal condition without the short circuit are different. So we have to calculate the current under short circuit conditions. That means we have to make use of this famous formula of the I short circuit. So I short circuit is I per unit times I line. But in this case, I line, okay, will be divided by 3 because that's the current we are going to find for each generator. So that will be the I line divided by 3. That will give us the I short circuit of each one of these generator. Okay, so I short circuit for generator 1 is equal to I short circuit for generator 2. That is equal to I short circuit for generator 3 because they are all equal in capacity. Okay, then that is equal to I per unit times I line divided by the square root of 3 because the I line here are all equal as well. Now, what is the I line here? I line here, remember now we are on the other side. We are on the primary side of the transformer. So, which means we're going to calculate our I line, okay, using the 33 kilovolt instead of the 132 kilovolt. So, from that, I line will then be equal to 50 MVA divided by 33 kilovolt times the square root of 3, and that gives us 874.77 amps. Okay, from there, I short circuit of the generator 1, 2, 3 will be 6 times 874 divided by 3. Remember, the 6 here is our I per unit, okay, that we calculated. Where did we calculate I per unit? Yes, here. That's the I short circuit divided by I line. That is the I per unit that we're getting from the secondary, from the short circuit there on the secondary. Remember, this is under the short circuit conditions, and from there we're getting a I short circuit from each generator is equal to 1749.5 amps. That is 1.7 kilo amps. Now you can see that each generator is supplying a bigger short circuit current than the entire short circuit current on the secondary. Why? Because obviously the short circuit current on the primary is going to be bigger because we are on the low voltage side. So the lower the voltage, the bigger the current. So the higher the voltage, the less the current, because this is a transmission line system. So that is it for this tutorial. I hope you guys really get a grasp of these protection circuit systems. So if you have any question, drop your question in the comment section, and stay tuned for more complex tutorials. This is still nothing, and there will be more complex tutorial coming. So until next time, cheers.